Okay, so here's some rules for working between logarithms and exponentials and solving some problems. Um, it's really not too bad. What you're going to do is you're going to follow the rule that we practiced uh, in the previous lesson, and that is just you're going to rewrite your logs and your exponents. So you can't forget that if you have some exponential equation, where you have a base b raised to the x power equals y, you can't forget that that's the same thing as the log base b of y equals x. Remember, the logarithm is equal to its exponent. Okay, so we're gonna need that property a lot. The other thing that we want to pay attention to is we want these bases to be the same. And if the bases are the same and there's an equal sign in there, then we can set the two exponents equal to each other. Okay, so the example they give us here is just if I have 3 to the x equals 3 to the 5th, then I can set this exponent equal to this exponent. In other words, x equals 5. And that's the only way that it's going to work. So down here on this first question, 4 to the x equals 1/2 x minus 3. Well, rewrite 4 to the x as a power of 2. Let's get it down to the simplest things. And so 4 to the x becomes 2 squared to the x. Rewrite the 1/2 as a power of 2. Well, that's the same thing as 2 to the negative 1. So we're almost there. Remember that, though, if you have variables outside in the exponent, then you're going to multiply them with all the things on the inside. So we're going to actually multiply these two guys together, and we're going to multiply these two guys together. So what I really have is 2 to the 2x equals 2 to the negative x plus 3. And so once I get here, I can set these exponents equal to each other, and I'll be able to solve for my missing value of x. So here we go. We're going to have 3x equals 3, or x equals 1. And always check this to make sure that it works out correctly. So if I have 4 to the first power, is that the same as 1/2 to the 1 minus 3 power? So this is 4. This is 1 over 2 to the negative 2, which is the same thing as 1 over 2 to the negative 2. Which is the same thing as 2 squared, which is 4. So that guy works out. Always check these guys. The next one, get them down to powers of 10. So we've got 100 here. That's going to be 10 squared. And then his power is going to be 7x plus 1. 1,000 is 10 cubed. So that's going to be 3x minus 2. So again, multiply the outside exponent with all the inside exponents. And you're going to have 10 to the 14x plus 2. And you're going to have 10 to the 9x minus 6. And again, once you get the bases the same, you just set those two guys equal to each other. So 14x plus 2 equals 9x minus 6. So this is going to be 5x plus 2 equals negative 6. So 5x equals negative 8. So x equals negative 8/5. And you can check that. We just want to make sure that we're going to get the exact same number from both sides. And so to check it, we're going to have 100 to the 7 times negative 8/5 power plus 1 equals 1,000. And then 3 times negative 8/5 minus 2. So you may need your calculator out to punch in some of these numbers, and that's certainly okay. And this is going to be 100 to the negative 56 over 5 plus 1. This is going to be 1,000 to the negative 24 over 5 minus 2. And you know what? You could probably just punch those right into your calculator. Exactly how you see them right now. So 100 to the negative 56 fifths plus 1 power is a really tiny number. 3.981 times 10 to the negative 21st. And the 1,000 to the negative 24 fifths minus 2 power is the exact same thing, so it checks out. Look at the next guy. So I've got 81 to the 3 minus x, so 81 is 3 cubed to the 3 minus x power, and that equals 3 to the negative 1 to the 5x minus 6 power. And so how do you handle these guys? Well, just the same thing. The outer exponent multiplies the inner, so I'm going to have 3 to the 9 minus 3x power equals 3 to the negative 5x plus 6 power, and the bases are the same, so I can set the exponents equal. So 9 minus 3x equals negative 5x plus 6, and this is 9 equals 8x plus 6, and this is 3 equals 8x. And let's see. I feel like I've made a mistake here somewhere. 81 is 3 to the 4th. I knew it. So this should be this is 3 to the 4th. So this should be 12 minus 4x. So this would be 12 minus 4x. That's better. So now I've got 9x plus 6 on the right, and on the left I've got 12. Should be 1. Gee whiz. Should be 1x plus 6 on the right. And then subtract 6 from both sides, and you get this guy. And again, check it. So this is going to be 81 to the 3 minus 6 power equals 1/3 to the 5 times 6 minus 6 power. And so you're looking at 81 to the negative 3 equals 1/3 to the negative 24th. So punch that into your calculator and make sure everything works out right. So when I do that, I get a really small fraction. .88 times 10 to the negative 6th, and then when I check 1/3, I get a really large number. which means then that I've got a mistake. So if you do this like you did your Algebra 1, and you were told to check and you checked it incorrectly, this is where you can run into some issues. So don't try and fudge the numbers then. Go back and see if you can't find the mistake in your problem. So when we're looking at our problem here, 81, double check that. What goes into 81? 9 and 9, and 3 and 3. So 81 is 3 to the 4th, and then 3 minus x, so 4 times 3 is 12. 4 times negative x is negative 4. 1 over 3 becomes 3 to the negative 1. So that should be negative 5 plus 6. So when I set 12 minus 4x equal to negative 5, there it is. There's my mistake. So it's really important to check, because sometimes you might get a solution that won't work, and sometimes you might have an error where we've got right here where my 5 should be negative. So if I make my 5 negative here, that's gonna change everything else. So 12 minus 4x equals negative 5x plus 6. And so now I've got 12 equals negative x plus 6. And so I've got 6 equals negative x. So negative 6 equals x. And now check that. You're going to get 81 to the 3 plus 6 power. And one third to the 5 times negative 6 minus 6 power. 81 to the 9th equals 1/3 to the negative 36th. So punch those into your calculator and double check. And I get a really large number that starts off this way for 81 to the 9th. It's going to be big. Let me see how many decimal places. 18. I get 18. And then 1/3 to the same power. There you go. And I got the exact same number. So check and make sure, so that you can make sure that you've got the right stuff going on. Alright, and the last guy to check is this solving the 4x to the 11th. And on this one, there's really no way that we can get the same base between 11 and 4, so we're going to come back up here to our relationship. And I'm just going to rewrite this guy. Remember, a logarithm equals its exponent. So I've got a log base 4, and my exponent is x. And so that means my 11 has to go inside. Well, what I've done is I've rewritten my problem now, and my exponent is not inside the my variable is not inside the exponent, and my variable is on the other side of the equal sign all by itself. So I can use my change of base formula to determine what this is going to look like. And so this would be the natural log of 11 divided by the natural log of 4. And so when you punch that in on your calculator, you get 1.7297. Alright, just like with the exponent rules, that if we could get the bases to be the same, we could set the exponents to be the same. We have the same rules for logarithms. If we could get the base to be the same on each side of the logarithm, then we could set the inside of the log equal to the inside of the log across the equal sign. And that's what we're looking for. So again, we don't want to forget about our relationship. If I have b to the x equals y, this is the same thing as a log base b of y equals x. Okay, don't forget this relationship either. And that's one of the reasons why it works, but then we can just say, hey, I've got x equals 7. So the other thing that we can do if we need is rewrite from an exponential to a log or from a log to an exponential. So let's just kind of look at some of these things. And like on the very first guy here, log base 4 of 5x minus 1 equals 3. I can't really rewrite that 3 as a logarithm of base 4. It's not going to work. So what I'm going to do is I'm just going to take my 4. I'm going to rewrite this as an exponential. So I have 4 to the third power equals 5x minus 1. Well, this I can do. I can do 4 to the third power. That's 64. And then I can work backwards here. So this is going to be 65 equals 5x. And so x is going to be equal to 13. Now, always check your answer on these because you cannot have a negative number inside a logarithm. And you're doing some complicated math. It's a good idea to check. We caught a mistake in our last problem by checking, so always do that. And what I'm going to have is I'm going to have log base 4 of 5 times 13 minus 1. And I just need to know if that's going to equal 3. So 5 times 13 is 65. And then I got a log base 4 of 64. And that's going to equal 3. And you can check that on your calculator by doing a change of base. You can check it by changing 64 to a power of 4. There's a lot of different ways you can do it. But this is good. This is a good check right here. And when you punch it in, you're going to get 3 equals 3. So on this next part, then, what we're going to notice is that we've got 5x over here, and we got x minus 1 over here, and equals a 2. Well, there's no logarithm where that 2 is, and that's okay, but there's a plus sign right here. And when you have a plus sign, that means that you're going to take the 2 logarithms and multiply the things on the inside. So this is actually going to become the log of 5x times x minus 1 equals 2. And so this is really log of 5x squared minus 5x equals 2. And this is a common log, so it's 10 squared equals 5x squared minus 5x. Divide 5, well, this is 100. And then we're going to divide 5 out of everything. And when you do that, you get x squared minus x equals 20. And since it's quadratic, we want to solve this. So subtract 20 from both sides. And then factor it and set each piece equal to 0. So I'm going to have 4 and 5. I'm going to have negative 5 and plus 4. So x equals negative 4 and x equals 5. Now, again, check this because you want to make sure that all your logarithms are positive. You cannot have a negative logarithm. So when I check out my original function, the negative 4, I've got log of 5 times negative 4. And right there, I'm done with this guy because I cannot have a negative number inside a logarithm. On the other side, though, if I've got log of 5 times 5 plus log of 5 minus 1 equals 2. That's what I'm interested in. So this is going to be, remember, you can multiply the numbers on the inside. So this is log of 25 times 4, which is 100, which is 2. On this last guy, this goes back to that first property that we were talking about today. And notice that my bases are the same on both sides of the equality. So I've got a base 5 here and a base 5 here. What that means is I can set the insides equal to each other. And so when I do that, I'm going to end up with 4x minus 7 equals x plus 5. And this is 3x minus 7 equals 5. And this is 3x equals 12. And x equals 4. And again, I've got to check that and make sure that I have no negative numbers inside my logarithm. So when I look at my log base 5 of 4 times 4 minus 7, that's going to be positive. And when I look at my log base 5 of 4 plus 5, that also is going to be positive. And then if you'll notice, this is going to be 16 minus 7, which is 9. And this is 4 plus 5, which is 9, so it works out.